Hey everyone, and welcome to today's Explainer. I am absolutely thrilled to jump into this one with you because we're looking at something that fundamentally changes how users interact with software. We're diving deep into the B4XDaisyAnimation class module. Now, if you've ever found yourself wondering how static, boring lines of code get magically transformed into these seamless, living, breathing digital experiences, well, you're in exactly the right place. This module, it's basically the secret engine behind that whole transformation.
So I really want you to think about this question as we get started today. What actually separates a clunky app from one that truly feels alive? We've all been there, right? You're using an application and moving from one screen to the next just feels jarring. It's rigid, and honestly, it makes the whole thing feel a bit cheap. But on the flip side, we've all used interfaces where every single button press, every menu swipe, and every page load feels incredibly smooth and natural. The difference there? It isn't magic. It's actually just math and optimization.
Here's a quick look at our roadmap for today. We'll start with the magic of UI animation. Then, pop the hood on hardware-accelerated B4X performance. After that, we'll break down the 3-0 pinner equations, check out the interactive easing playground, and wrap up with crafting better user experiences.
All right, let's kick things off with Section 1, the magic of UI animation. To really wrap our heads around this module, we kind of need to reframe how we even think about moving pixels around a screen. When we use the B4XDaisyAnimation module, we aren't just saying, hey, move this button from point A to point B. We're actually simulating the physics of the real world right inside a digital space. Think about it. When an element drops and uses a bounce effect, we are literally simulating digital gravity. When a menu stretches and snaps into place using an elastic effect, that's tension. And when a screen slides in super fast but then slows down right before it stops, which we call an ease out, we are simulating friction. Giving these UI elements real-world weight is exactly what builds that instant user intuition.
Moving right along to Section 2, Hardware-Accelerated B4X Performance.
So you might be wondering, how do we actually make this physical simulation run so smoothly without totally draining the device's battery or, dropping a bunch of frames? Well, if you dig into the source code for B4XDaisyAnimation, you'll see it doesn't rely on those standard, clunky software-based timer loops to push things around. Instead, it dives straight into the native Android API using a Java object reflection layer. By calling the animate method directly, the module taps right into the device's view property animator. It's essentially bypassing the middleman and handing the animation instructions directly to the graphics engine itself. This means all those heavy calculations get offloaded to the hardware. The result? Buttery smooth performance that handles simultaneous fading, scaling, and translating without breaking a single sweat.
And this perfectly illustrates how the module protects developers from some really obscure platform quirks. Take a look at this incredibly clever helper sub called Safe Duration MS. So when you're using Java Object Reflection to set the animation duration, the native Android method expects a primitive long data type. If a developer accidentally passes a standard integer, the method matching actually fails behind the scenes. But here's the totally crazy part. It doesn't crash. Nope, it just silently ignores your custom duration and falls back to a default of 440 milliseconds. By centralizing this fix in a helper sub that automatically boxes that integer into a long, this module literally saves developers hours of pulling their hair out trying to figure out why on earth their timings are wrong.
All right, Section 3, the 30 Penner Equations.
So, now that we have this powerful hardware-accelerated engine, we need to talk about the steering wheel. The mathematical flavor that gives all these animations their unique, distinct character comes from the Robert Penner easing equations. The module includes this dynamic evaluation engine for 30 different easing curves, which, okay, I know sounds super overwhelming at first, but they actually follow a really logical structure. You basically just have a curve style, like quad, quart, bounce, or elastic, and then you apply a modifier to it. In just means the animation accelerates from a total standstill. Out means it decelerates as it approaches its target, and in-out, well, it accelerates halfway and then smoothly decelerates. It's really just math dictating the flow of time.
The truly crucial point, though, is how you apply these to real-world user interfaces. Let's take easeOutElastic as an example, straight from the module source notes. Say you want a menu to pop onto the screen and slightly overshoot its target before vibrating back into its final resting place. You'd use an elastic curve. As the notes point out, this specific mathematical equation is absolutely crucial for modern UI components, like the floating drawer or those dynamic boom menu effects. It perfectly mimics the physics of an actual physical spring snapping into place.
Let's jump into Section 4, the interactive easing playground. Look, trying to visualize a cubic polynomial equation in your head is pretty tough for anyone. But the beauty here is that you don't have to guess the math. You can literally watch it happen in real time. Notice how this live visual graph plots the progression of the easeOutBounce curve. Visually, it looks exactly like what it represents: a rubber ball dropping from a height, hitting the floor, bouncing back up a few times with diminishing returns, and then finally settling down. Being able to see that curve drawn out as the animation plays, it takes all the guesswork completely out of UI design. And to make things even easier, the playground organizes all 30 of those complex math equations into really digestible, categorized buttons. Want to see the difference between an exponential curve and a circular curve? You just tap the buttons. Curious how a back overshoot feels compared to an elastic snap? You can test those different physical feels instantaneously. It's honestly a phenomenal tool for rapid prototyping.
Finally, bringing it all together in Section 5, crafting better user experiences.
By combining that hardware acceleration we talked about with precise mathematical easing, developers can craft vastly better user experiences. And the B4XDaisyAnimation class doesn't just stop at the basic properties. It does the heavy lifting for you by combining them into these really complex, multi-property combo animations. With literally a single line of code, you can trigger animations that mimic the incredibly popular Android View Animations library. We're talking about really fun, attention-grabbing effects like ta-da, rubber band, and shake. You can pull off complex view transitions like zoom slide, where a view shrinks and slides out simultaneously, or even 3D effects like accordion and cube swings. I gotta say, my personal favorite is the hinge effect, where a view literally swings from the top left corner as if a physical hinge just broke, and then it drops off the screen entirely, which honestly is exactly how I feel at the end of a long week of debugging. To manage all of this magic, the module utilizes dynamic directional handlers. These routines expertly manage the X and Y offsets, figuring out whether an element should slide in from the left, drop from the top, or flip along a specific axis. And the attention to detail here is just fantastic. For example, in the Animate Flip directional sub, the code explicitly injects a native command to set the camera distance to 12,000 pixels. Why? Well, because during a 3D flip animation, if the camera is too close, the corners of your view will visually clip right through the screen boundaries. This single line of code completely prevents that 3D clipping, making sure your flips look polished and super professional on any device.
Which brings us to the end of our journey today, and leaves us with this pretty exciting question. Which easing curve is going to define the feel of your next app? We've explored the hardware engines, dug into the 30 mathematical curves, and checked out the playground that lets you visualize it all. The power to turn static, lifeless code into a totally dynamic, physics-based user experience is sitting right there in the B4XDaisyAnimation module. I highly encourage you all to jump into that easing playground and just start experimenting to find that perfect physical feel for your next project. Thank you so much for hanging out with me for this explainer, and hey, happy coding!